Okay, guys, so we are going to get started on Chapter 3 today. I'm going to put Chapter 3 Sections 1 and 2 together because this should be a review for most of you. If you have any trouble, please let me know, but we're going to jump right in, okay? So, in Chapter 3, we are talking about matter. So, let's get going here. Now, I have linked this in the activity, so if you just want to go and print off your notes, that is perfectly fine with me. I can't print for everybody because I just don't have that much toner. So if you have any issues with taking notes, just let me know. These are quick little buttons so you can get to each section. We're going to do section 1 and 2 today. So section 1, so I call this 3.1. And this is properties of matter. So we're going to talk about physical and chemical properties of matter. Now, when we're talking about properties, we're talking about what state is it in, so solid, liquid, gas, and the other things that help us describe the matter itself. What does it look like? Qualitative stuff, quantitative things. What about chemical properties? What does it do when it's mixed with other things? How does it bond? So take a minute and think through. What do you know about physical and chemical properties? Take a minute and always pause me if you need to. Here are essential questions for this section. What characteristics identify a substance? What distinguishes physical properties from chemical properties, and how do the properties of the physical states of matter differ? Hopefully you know most of this, but our review vocabulary, I got it, don't worry, is density. So let me remind you that is a ratio that compares the mass of an object to its volume. So we take our mass and we divide by volume. The derived units there are grams per milliliter or grams per centimeter cubed. Remember, derived means that we're combining two different units. So mass and volume, that's grams and a volume unit. So it's derived. Take a look with me on page 68. Push pause if you need to get your book or ebook open. On page 68, you'll get a good look at the three different states of matter. So when we're talking about gas, we're talking about the air above us and how it moves. And you can see in that little picture there that it's moving very rapidly for a gas. Then it has a zoom in of the liquid, and if you notice, there's not much order to it, but it is much closer together because the volume of a liquid is smaller. And then for a solid, anything that's a solid has a rigid, uniform shape to its components. However it's put together, there is some order to those molecules or atoms. So the little inset at the very bottom corner says about 70% of Earth's surface is covered with water. Water is the only common substance on Earth that exists naturally as a solid, a liquid, and a gas. So we see ice at the polar regions or during winter. We see the liquid all over the continents, or not continents, all over the oceans. And then we see the gas just in our clouds that have condensed above us. So we're going to flip the page. You are now looking at page 70, properties of matter, and we're going to get going. We got a lot of vocabulary here, but most of this you already know. The few that I'm going to hone in on here are vapor, physical property, not physical property, intensive properties, and extensive properties. So those are down at the bottom. Those are your really big new terms for this section. Let me remind you that matter is anything that has mass and takes up space, and it's everything that we see around us. Matter with a uniform and unchanging composition is a substance. So something that no matter how much or how little that I have, anytime I zoom down to the molecular level, it's always going to be uniform, and there won't be any other little particles mixed in with it like a mixture. So a substance is the same throughout. It is literally the same molecules, or it's the same atoms rearranged in a certain order. So we have three states. So solid, liquid, and gas are what you're used to. I'm not going to lie, there are two more. There is plasma, which most of you know by now. And then there's the last one that we reach when we get down to absolute zero, and that is called the Bose-Einstein condensate. So those are two more, but they're not common enough for us to spend much time on. So remember, solids are a form of matter that have their own definite shape and definite volume because they're stuck in this rigid solid material. Liquids take the shape of their container, but they do have a definite volume. We can calculate the volume there. And gases have no definite shape and no definite volume. They expand to fill any container that they're in. So, what is the difference between vapor and gas? Well, I'm glad you asked that. Vapor refers to the gaseous state of a substance that is normally liquid or solid at room temperature. So when I talk about water, water or H2O is a liquid at room temperature. So when I boil water, I don't talk about the steam that comes out of it as a gas. Technically it is, but it's technically a vapor because it's been changed from the liquid form. So a gas is something like nitrogen or oxygen or CO2 in the air, things that are naturally gases. But a vapor, if it came from a solid, if you've melted it and then boiled it, or if it came from a liquid, it has evaporated or boiled off, which are two different things. We'll go over that. Then it's considered a vapor. Okay, then it's considered a vapor. Okay, so you need to pause me now, and I would like for you to take a good look at all of the pictures on page 70 and 71. They are very important, and I really think that that helps everybody to understand. I'm going to move ahead now, so pause me if you need. So let's go talk about physical properties. Physical properties are observed or measured without changing the composition. So if I can tell this or if I can measure this without messing with the actual structure of the material, then it's a physical property. So here, what are some physical properties of, let's say, oxygen? Oxygen, if you'll look down here, is colorless. At room temperature, which is 25 degrees Celsius, it's a gas. Its melting point, I can check that without changing it. It's still oxygen no matter what phase it's in. Melting point is negative 219 Celsius. Boiling point is negative 183 Celsius. And its density at room temperature, remember that changes with temperature, is 0.0013. So obviously it's much less dense than most things that we talk about. Let's go down here and look at sodium chloride. Sodium chloride is NaCl, so that is normal table salt, and we normally iodize it because we're usually iodine deficient. So don't worry, it's just normal table salt. What color is it? Well, it's white. At room temperature, it is solid. The melting point, if you want to melt, not dissolve. If you want to melt sodium chloride, I just had a pan with a whole bunch of salt in it, it would have to get up to 801 degrees Celsius. That's really hot. The boiling point is 1465 Celsius. Really, really hot. And the density at room temperature is 2.17 grams per centimeter cubed. So you can see here all of this stuff tells us these common properties of substances you're used to. So mercury, what used to be in thermometers, water, clearly we know what that is. Notice this is why we have Celsius, it's 0 to 100. It's always a liquid between 0 and 100. And sucrose, that's just table sugar, white, solid, melts at 186, a little lower, we'll go over that, but it decomposes before it's going to boil. So that's kind of interesting. And it has a lower density than salt. Okay, that's a lot of information, but keep in mind, physical properties are properties you can determine without altering the substance itself. That falls into two categories. If it has a value, or if that property changes with the amount that you have, it is called an extensive property. So your biggies are mass, length, volume, things that when I measure, that number is going to change based on the sample size I have. I could have enough to hold in my hand, or I could have like a big old chunk of it that's bigger than my face. Those are going to change about table salt or about sugar. A big block like this versus a little block that fits in my hand, they're going to have different masses, different lengths of sides, and different volumes. Now, will the fact that it's white ever change? No. Will the density change because the mass got bigger but the volume got bigger? So remember, the density shouldn't change if you're at the same temperature. Those are going to be intensive. And I think about intensive as it's inherent to the substance. So the salt itself, something that I'm not going to change about salt unless I do something chemically. I'm never going to change that it's a white solid at room temperature. That's intensive. It's never going to change. But I can change the amount that I have, and that changes those measurements that we looked at. Density doesn't change. Melting point and boiling point don't change, but the density won't change unless you change your temperature. So intensive are like your qualities, like does it conduct electricity? What color is it? What state is it at room temperature? Those are all intensive. You may want to back this up because I'm talking very quickly, and make sure that you got all of that, because this is the hard part and this is the part most people miss on the quizzes. Chemical properties of matter. So the ability of a substance to combine with or change into one or more other substances is called a chemical property. This changes the subject. Clearly, if it's a chemical change, I'm not going to get what I had back. So examples, iron forming rust. I can't get that rust, that iron oxide, back to iron without doing another chemical change, without changing the structure of the atoms. Copper turning green, that's called oxidation. The Statue of Liberty is now green. I could like sit there and sand her down and I can get all the green patina off of it, but that little bit that has already changed to copper oxide is never going to go back to copper, okay? It's not naturally going back. So that act of oxygen on the copper or on the iron has changed the composition and it's not going back. Other examples, combustion, mixing with acids. Anytime it's going to have an actual chemical change, and I'll show you how you know those, that is a chemical property. So oxidation, combustion, those types of things are chemical. I'm not getting it back. All right, so observing properties of matter. A substance can change forms, but you have to be careful because that can be physical or that can be chemical. Ice going to water, going to steam. That is a physical change because it's all water. So it can change form but still be physical. Let's go talk about chemical properties. If I mix water with sodium, it's an explosive reaction and I end up with what we call sodium hydroxide. And that is not going back to pure sodium and pure water because of the change that has occurred. So keep in mind a lot of things happen at the right temperature and pressure, and we'll go over that a little more when we talk about gas laws. But if you look down here for copper, physical stuff, stuff that doesn't change the composition. I can tell you it's reddish brown and shiny. I can tell you it's shaped into sheets or malleable, so I can hit it with a mallet and lay it flat. I can draw it into wire for electric units or, housing units. And that is what we call ductility, if I can draw it into a wire. These are terms you're going to need to know, if those two in parentheses there. It's a good conductor of heat and electricity. We'll talk about why later. It has a density of 8.96 grams per centimeter cubed. Measuring that doesn't make me change it. And then the melting and boiling points are listed. They're really high as well. Take a look at the chemical properties. These all change the substance to some new substance. So chemically, it will form green copper carbonate when in contact with moist air. Oh, so it's copper carbonate, excuse me, I was wrong. I said copper oxide. It reacts with nitric acid and sulfuric acid to form new substances. And one type of compound forms a deep blue solution when in contact with ammonia. Those are all chemical changes that change the makeup of the substance for me to be able to tell you. Okay, what characteristics identify a substance? What distinguishes physical from chemical? And how do the properties of physical states differ? So think solid, liquid, gas. How are those different? Think about particle motion. Think about organization. How close are they together? How quick are they moving? And there's all your vocab. All right, so section 2, we're doing changes in matter here. So take a second. If you needed to go back, go do that real quick. I'm moving as quickly as I can to keep this short. So if you need a second, take it. Okay, so the main idea in section 2 is that matter can undergo physical and chemical changes. So remember, we talked about properties. What is it like? What does it do? And now we're going to talk about the difference in those changes. These kind of blend together with last section. Your new questions: what is a physical change and what are some common examples? What defines a chemical change and how can you recognize it? And how does the law of conservation of mass apply to chemical reactions? So at this point, we need to be on page 76 in your book or ebook. And you'll see a lot of pictures here: condensation and solidification. We call that freezing. And then we're going to go talk about the chemical changes on page 77. And we'll get to that in just a minute. Okay, so let's talk about let's talk about observations first. Observations are what we're being able to tell from studying or looking at things. And the definition here is orderly, direct information gathering about a phenomenon. So whether that's that condensation where I see water forming on the outside of a cold can, or whether that's freezing of water in the form of icicles during winter. Okay, so yeah, we're ready to go. New vocab. Physical change is a change that alters a substance without changing its composition. We talked about that a little last class. Be sure you get that down. Also, a phase change is a transition of matter from one state to another. Now, here are the phase changes you need to know. Here are some, and I'm going to pull this up in a second, and hopefully you're ready. Boiling, freezing, melting, and condensing are all phase changes that we use. But there are a couple more that you are responsible for. So pick up your pencil with me. Hopefully you got your definitions. If not, back me up. And we're going to talk about the phase changes you're responsible for. So I'm just going to write gas. It may technically be vapor. Okay, so as I go from a solid to a liquid, what is the name of that phase change? From solid to liquid, it's increasing in energy. So over here, energy is increasing this direction. The particles are increasing in energy. So when we go from solid to liquid, we call that melting. They're gaining energy as the particles. So that is what we call endothermic. If it's going up, it's endothermic. I can't write sideways, I'm sorry. And then if it goes from liquid to gas, the particles are gaining energy again, and we call this vaporization. Now, that is the same concept as boiling, and it is different than evaporation. Let me talk for a second about evaporation. Evaporation is a phenomenon that happens, let's say this is the top of the water. It only happens to the top layer. Evaporation happens layer by layer. So that's why if there's a puddle outside, then if I'm talking about it, it's going to evaporate layer by layer by layer. Boiling is different. Vaporization is different. Vaporization is the whole thing is boiling from bottom to top. So vaporization is an active form of phase change. We are boiling the whole thing. That's why when those bubbles start forming in the pan when you're trying to cook, that's the start of vaporization. The whole thing has reached the boiling point, which for us is 100 degrees Celsius because we're normally boiling water. Evaporation is passive. It happens layer by layer as the top particles are getting hit by sunlight. They are getting more energy, and as they get enough energy, they break away from the rest of the liquid. Down here at the bottom, we're applying heat, and the whole thing is heating at the same rate. That's how they're different. Now, if I go straight from a solid to a gas, that is endothermic as well, and it is called sublimation. I'm sorry, my handwriting's so terrible today. I apologize. So that is called sublimation. So solid to liquid is melting. Liquid to gas is vaporization, and solid straight to gas is sublimation. This doesn't happen super normally. So think about dry ice. When dry ice is exposed to air and as it starts to heat, it doesn't form a liquid at all. All it does is send the gas off, okay? Let's go the other direction. If I go down in energy, this is called exothermic. It releases energy and it cools. Let's start from the top. If a gas goes back to a liquid, that's called condensation. If a gas goes back to a liquid, that's condensation. If I had a really nice can of a Coca-Cola product and it were cold and I left it sitting right out in the sun, it would start to form water droplets on the outside because that can is cooling the air right around it, and that water vapor in the air is condensing and forming on the can. So let's go back down again. If liquid goes to solid, that is called freezing. Freezing. Hopefully you can spell freezing better than I can. So as it loses enough energy from the liquid particles, they stop moving as often and they become stuck in a solid formation. So that is called freezing, and it's a loss of energy. Now, when gas goes directly to solid, you don't see this often. This is called deposition. And the best way I can explain deposition is to say, like when you open a big chest freezer or a large stand-up freezer, if you open it and all that vapor comes out at you because it's so cold and you can see it as it moves through the room. Well, if you think about it, when you close that back, all that gas that was moving around has to go somewhere. So what does it do? Well, against the wall of the freezer, it attaches again. And that's called deposition, okay? That gas deposits on the walls of the freezer as what we call freezer burn. So it just attaches right back there. That's why you don't want to go opening and closing freezers a whole lot, because you're going to cause a buildup there. So if you don't have all of these, and hopefully yours is prettier than mine, please take a second and get that. You need to know that exothermic is when it's lowering in energy, so it's going from a high energy state to a lower. And endothermic is when it's going from a low energy state for the particles to a higher energy state. So they're moving more if it's endothermic. If it's exothermic, you're slowing them down, okay? Take a minute and write down any questions you might have. Okay, so we went over our phase changes. Again, those don't change the substance itself, it just changes the organization of the molecules or atoms. Chemical changes. A chemical change is a change that involves one or more substances turning into new substances. I can't get it back. So with physical, all I had to do was heat it up or cool it down, and it's still that substance. For chemical, if I change that organization completely where new stuff is attached to new stuff, I'm not getting it back. So when we talk about decomposition or rusting, that's oxidation. You write down oxidation for rusting. Exploding, burning, or combusting, those are all terms that describe chemical changes. If I also say something reacts with something, that's a chemical change occurring and a chemical property that it can. Let's talk about the law of conservation of mass. It states that mass is neither created nor destroyed in a chemical reaction. It's always conserved. So here's the tricky part. Whatever I start with mass, no matter how it changes, as long as I keep it in a closed system and measure it again at the end, the mass will be the same. So if I start with 5 grams of hydrogen and I add 5 grams of oxygen and I get them together under the right pressure and temperature, I'm going to make water. But since I had 5 grams and 5 grams, I'm going to have 10 grams of water. So that's what you need to know. We never lose anything. We're just rearranging the bonds that hold things together. If it's not a closed system, you may not be able to measure it. So if something were to bubble out, say I mixed vinegar and baking soda and it bubbles up, I'm losing that vapor. But if I could trap it and measure it, you would see that we're always going to have the same mass beginning and end. Let's go do a problem. In an experiment, 10 grams of red mercury 2 oxide, and we'll talk about that later, is placed in an open flask and heated until it is converted into liquid mercury and oxygen gas. The liquid mercury has a mass of 9.26 grams. So what's the mass of the oxygen formed? So I start with 10 grams, and then I get 9.26 grams of the mercury, and this was mercury oxide. Excuse me, I'm going to shorthand this. So how much oxygen's left? Well, just subtract and you'll find out. It's like putting X here. So what is 10 minus 9.26 grams? I am going to put X, so excuse me. 10 minus 9.26, don't have my calculator, got to use my phone. I get 0.74 grams, which is good because I need 2 decimal points because each measurement had 2 decimal points and we're subtracting. What's the mass of oxygen? It's 0.74 grams of oxygen left. And that doesn't seem fair, but we'll go over why there's so much more mercury at the end of this in a little bit. So, law of conservation of mass. Reactant plus reactant, and this is simplifying it, is equal to products. Okay, so this side will equal this side, no matter how many things are on either side. If you have any questions, write those down and you'll give them to me at the end of this. So what are the essential questions? What is a physical change and what are some examples? We went over it. I drew the big triangle for you. What defines a chemical change? We talked about that. And how can you recognize it? So when we're talking about recognizing a chemical change, we are talking about we'll get back to that, but just keep in mind you're going to have a new product than you had, and that new product has new properties. Think of burning wood. So that action of burning wood, or the combustion of wood, I need the wood and I need oxygen, and as that reaction's occurring, then I'm going to get ash. Ash is not like wood. Ash will never burn again. So you can tell that they're 2 totally different substances. Okay, I think that's about that. So if you have any question, oh, and law of conservation of mass, keep that in mind. If you have any questions, please email me, but that's the end of this lesson.